The next section on the chemical equilibrium chapter is the reaction quotient. The reaction quotient is pretty much a tool that you can use to make predictions regarding the position of equilibrium. So let's say in the previous problems we were telling you, well, you have this initial condition and then you have this final condition or equilibrium condition, and then you can start your calculation based on that. But what if I give you that initial condition, but I don't tell you absolutely anything about that being actually the initial condition or an equilibrium condition or any other condition within the reaction? So how can you start solving your problem if you don't have that information, if you don't know what's going on with equilibrium? Well, the reaction quotient basically is helping you with that. So think in terms of the reaction quotient to be something that you want to use for prediction. So prediction power in terms of what is going on with that equilibrium reaction. Okay? So basically you want to compare that reaction quotient is something that you calculate based on whatever condition you are being given. You don't really care whether it's an initial condition or an equilibrium condition, because the reaction quotient will tell you what is that condition. Okay, so here we just want to compare that value of Q, the reaction quotient, to the value of the equilibrium constant. So in the calculation of this reaction quotient is very simple. If we have our generic equation A plus B going C D, then the reaction quotient, if you are using concentration, then it looks like this. And if you're using pressures, it looks like this. And you may be asking yourself, well, that looks awfully familiar, right? And yes, it looks familiar because if you write the equilibrium constant, then the equilibrium constant is going to be C D A and B. And the same goes if you are using the pressures. The expression, what you are looking at here, is that the expression of the reaction quotient, it's exactly the same as the equilibrium constant. So then you may be asking now, well, and then what is the difference? The difference is simply that for the reaction quotient is any concentration you absolutely don't care about their initial, their final, their whatever. They could be anything. You can use, in that equation, you can plug in absolutely any given concentration that you have at hand. However, for the equilibrium constant is strictly equilibrium concentrations. Okay, so the thing is, whatever value you are calculating here, if you don't know that they are equilibrium concentrations, you cannot assume that that calculation is giving you the equilibrium constant, but a reaction quotient. Okay, so that's the main difference between those two, but mathematically they look absolutely the same. It's the same protocol, it's the same equation. It's just what values for concentration you are plugging in on those equations. Okay, so we are talking about comparing the reaction quotient with the equilibrium constant, right? So what are the situations? Well, Q could be larger than K, Q could be smaller than K, or Q can be equal to K. So depending on where the value of Q falls, then you have a different conclusion. So first one, let's take a look at what if Q is larger than K. So that means, remember, let's use a simple reaction here. So let's say we have A goes to B. Therefore, Q is B over A. Okay? So if Q is larger than K, that means either B is too large or A is too small. So that means you either have to decrease B or to increase A, or both at the same time. Therefore, since B is the product and, wait, this is an equilibrium reaction. If B is the product and you have to decrease B or increase A, then the reaction is going in that direction. So if you calculate Q and it turns out that Q is larger than K, then the reaction is you are not at equilibrium and the reaction is moving towards the left, or is shifting left, meaning it's favoring the reactants, okay, so that you decrease the value of Q. So therefore, products will decrease, reactants will increase. Now, if you have Q less than K, okay, if Q is less than K, then let's focus again here. If Q is less than K, it means that either B is too small or A is too large. Therefore, you have to decrease A and or increase B. Since your reaction is A going to B, then if the condition is that Q is less than K, you have to favor the products and the reaction is shifting to the right. Okay, therefore, the products will increase and the reactants will decrease. It's the opposite, okay? Q larger than K, you're favoring the reactants. Q less than K, you're favoring the products. Last but not least, if Q is equal to K, well, you use concentrations that are giving you a value of Q that is equal to the value of K. Therefore, you are at equilibrium. Okay, in terms of shifting, nothing is going to happen because your reaction is already at equilibrium. There is nothing to change. The concentration of the product, the concentration of the reactants will not change a bit. Okay? Now, these are the common cases, but there are a couple of special cases. So what if you have Q equals 0? And let's go back to our initial, our simple equation. So when is Q equal to 0? Well, either B is equal to 0, most likely, or A is extremely, the concentration of A is extremely large. Okay. So therefore, if you have Q equal to B over A, if B is 0, then this is 0, right? There is only one way to proceed here. If you don't have any of the products, the only way to go is producing products, right? So your reaction has to go in the forward direction, okay? Shifting to the right or favoring the products, okay? Let's write that. So favoring products, shifting right. Think of them in terms of synonyms. Okay, favoring the products is the same as saying the reaction shifting right, or this is forward direction favored. Any of those is conveying exactly the same information. Okay, so that is if Q equals 0. Now, what if you have a condition in which you go A equal to B, but now concentration of A equals 0? No, that's not what I wanted to do. Concentration of A equals 0. So your reaction quotient, if A is equal to 0, then this is infinite. Okay? Or undetermined. But now think about it. If you don't have any of the product reactants, then the reaction can only proceed in one way. So if you only have products and none of the reactants, then that reaction is going into the reverse direction. Okay, so when Q is infinite, then you are favoring reactants, or you can say the reaction is shifting left, or you say that the reverse direction is favored. Okay, any of those are the same. Okay, so those are the simple cases when you have when you are comparing the value of Q with the value of K. If we want to see this in a graphical view, okay, this is, remember here we have Q or K. More specifically, this red line, that is the value of K. So that equilibrium will move up to having concentrations that obey that equilibrium constant. And here are your cases. So this is Q equals 0. And let's divide this. Okay, we are right here. On this side, Q is less than K, and on this side, Q is more than K. Okay, so if Q is larger than K, then you are trying to go to the opposite direction. So you want to favor the concentration, the reactants, okay, and in this direction you are increasing the products, in that direction you are increasing the reactants. So if you are going in this direction, you are decreasing products and increasing reactants. If you go in that direction, you are increasing products and decreasing reactants. Okay, so the point, that reaction will be moving until you reach that point. That is the equilibrium point. Okay, and up here is Q infinity. Okay, so how do we use this in practical, as a practical approach? So we have Kp here, and remember, when it comes to equilibrium constant, you can use either pressure, you can use concentration. In this case, we have Kp, so we're going to use pressures. And in this case, what I was saying, so reaction mixture contain these pressures of each one of those substances. Is it at equilibrium? We don't know. Is that an initial condition? We don't know. So we have to calculate Q in order to determine whether that's an equilibrium condition or not. And if so, if it's not an equilibrium condition, in what direction is this reaction moving? So here Kp is going to be the pressure of ICl squared divided by the pressure of I2 times the pressure of Cl2. Okay, so if we do that calculation, okay, this is what we have here. So remember, pressure of I2 is equal to 0.114. We can forget about the units for now. Pressure of Cl2 is 0.102, and pressure of ICl is 0.355. Okay, so this value goes here, this value goes here, which is the PCl2, and this goes here. So when you obtain that value, Q is equal to 10.8. So 10.8 versus 81.9. So the conclusion is Q is less than Kc. And what happens when Q is less than Kc? Well, that means you are favoring the products, which means in this case, if we are using pressures, then the pressure of the products will increase and the pressure of the reactants will decrease. Okay, so the reaction will proceed to the right. So again, remember, shifting right, or the forward reaction is being favored. Okay, so the point is you will increase the concentration of products, you will decrease the concentration of reactants. Why? Because the value of Q is less than the value of Kc. And another meaning that you can have that is that you can say that either the pressure of the products is are less than they are supposed to be, or the pressure of the reactants is larger than they are supposed to be. So you have to decrease the reactants, you have to increase the products. So we have another example here. So in this case, whenever you have a reaction, you don't really need to write everything that is in the reaction. I mean, we can make this a lot simpler. So we can possibly take this reaction, and if you feel comfortable with it, please by all means do it. But we can just say that this is A going to B, just to make it simple. Therefore, here Q or K is going to be equal to concentration of B squared divided by concentration of A, which means this is B and this is A. So you have to follow, okay? Yeah, again, if you feel comfortable with that, please do it. If not, then write everything that you see there. So Q is going to be equal to B squared 0.0255 squared divided by 0.0331. And in this case, we have 0.0255 squared divided by 0.0331. And this is 0.0196, or 196 10 to the negative 2. Now we compare this to 585 10 to the negative 3. The conclusion is Q is larger than Kc. And as such, if Q is larger than Kc, then there is more product than it should be compared to the reactants, and therefore this reaction is going to the left. Okay? Is shifting left. You are favoring the reactants, you are decreasing the concentration of products because Q is larger than Kc. Okay, so that's what there is to reaction quotient. Remember, it's a particular tool to predict what's going to happen with the equilibrium, or what's going to happen with the reaction, where how far, that's another term that you can use, how far you are from the equilibrium and in what direction you have to move the reaction is so that you get to the equilibrium condition. Okay.